Hello and welcome to my talk. My name is Thomas Nindl. I am affiliated with the Charles University in Prague in Czech Republic and with Berufsakademie Sachsen in Dresden, Germany. The title of my talk is A Gradient-Based Framework for 3D Print Appearance Optimization. 3D printing has thoroughly disrupted the manufacturing industry. There's many applications and I'm sure you can name a few of them. There is, for example, creating architectural models. There is 3D printing obscure spare parts that are not used very often and therefore very expensive to keep in stock, or custom prosthetics. There are several technologies available for doing 3D printing, such as FDM, SLA, or multi-jet fusion. And for this talk, we are going to focus on a particular technology that is called polyjet printing. Polyjet printing works akin to how your inkjet printer at home produces images. Tiny drops are deposited on the building surface and immediately hardened by applying an ultraviolet light. Repeating this process along the z-axis then produces volumes that are made from tiny voxels of different materials. There's many materials available that differ either in their mechanical or in their optical properties. For this talk, we are going to focus on the optical properties, and there is several materials available in the basic colors of subtractive color mixing, which are, of course, cyan, magenta, yellow, black, and white. And there's also a transparent material available. Because the materials are translucent, you can, by clever spatial arrangement of the materials, create almost arbitrary colors. So the translucency enables the color mixing, but it also creates a challenging problem. How do you arrange the voxels to faithfully reproduce an object's color and general surface appearance, while at the same time limiting unwanted effects of the translucency, such as blurring and low contrast? Naively placing the inks, for example, by just extruding the texture into the volume, as you can see here in the image, is not sufficient. Compare that to the results of our framework and you can see what is possible by carefully optimizing the spatial configuration of the printing materials. There has been quite some work in the area, of course, and we can basically put it into two different categories. There is the forward-only approaches and there is iterative pipelines. In 2015, Brunton and others were the first to show high-quality, full-color 3D polyjet printing with faithful color reproduction based on a generalization of half-toning. Our pipeline is capable of doing the same, while very easily generalizing to arbitrary material sets. Babai and others developed a method that greatly reduces the half-toning artifacts by driving stacks of inks into the volume in a certain order, and this is made possible by exploiting ambiguities in the volumetric color mixing. These ambiguities will play an important part for our method as well, as we will see later. Later in 2018, Brunton and al. Show how to make deliberate use of the transparent materials. They use them to control subsurface scattering and fabricate objects that have transparent parts. Our method is also capable of doing the same and take full advantage of the available transparent material. Looking at the iterative approaches, the first that appeared was in 2017 by Alec and co-authors, who presented a method that substantially improves contrast and sharpness of the printouts. They use predictive rendering in concert with a heuristic refinement step to iteratively converge to a solution. This work was later taken further by Sumin and others in 2019 and Rittich and others in 2021, respectively. Like the method of Alec, Sumin, Rittich and others, our approach also uses iterative optimization. But in contrast to their method, where a heuristic is used to change the configuration of the materials inside the volume, we want to frame the problem as a general optimization problem. So let's take a look how their pipeline works. It starts with a geometric discretization into volume element called voxels, and then the iterations consist of a half toning, a predicting, and a refinement step. Now, a unique feature of this pipeline is the fact that the prediction is based on a half-toned volume, so each voxel has exactly one material assigned. This is a good model for what the printer is actually doing, but this would make the optimization problem an instance of integer programming. Considering that a typical printout has millions of voxels, or maybe even billions, this problem quickly becomes computationally prohibitive to solve exactly. So our first key idea is to move the half-toning out of the optimization loop and replace it with a volume parameterization that is based on continuous material mixture. This relaxes the problem to a nonlinear, non-convex optimization problem. So we can apply gradient-based optimization to solve it, and for this we also need derivatives for the prediction step of the pipeline, and we get them by applying a technique that is called differentiable rendering, where recent advances made large parameter sets computationally feasible. Okay, so now that we have derivatives, we can replace the refinement step that was previously heuristic in nature with a cost function. And in our case, we use a custom error metric for that, which allows us to steer the optimization into certain directions, for example, favoring more the color accuracy or favoring more the sharpness and contrast of the object. So the key contributions of our work are the following. First, we present a flexible and robust framework for PolyJet 3D print optimization based on a numerical method. This allows us to integrate aspects that were previously required specialized solutions into one consistent framework. Second, we propose a volume parameterization based on material mixtures that enables global optimization and easily adapts to arbitrary material sets. And finally, we show generality of our pipeline with respect to the optimization goal, to the available printing materials, and the geometry of the object. So let's take a look at the ingredients a little bit closer and start with the prediction step. Each point in the volume has certain optical properties assigned. One way of parameterizing this would be using the absorption scattering coefficient and a phase function. And to calculate an appearance, you could, for example, use a path tracer. So you would start tracing paths through the volume and simulate scattering and absorption event, and you would do that many, many times and eventually converge on an estimate of the appearance of what the eye would actually see. Our algorithm does not only need to know the appearance, but also its derivatives with respect to all volume parameters involved in light transport. This is called differentiable rendering, and we are using a particular flavor of differentiable rendering that is called radiative backpropagation. The derivatives are then used in conjunction with a gradient-based optimization algorithm to find a voxel configuration that reproduces the target in the best possible way. In essence, our approach is to frame the problem of 3D print optimization as a very large inverse rendering problem. Instead of using images taken from different camera angles as an input, we just use a target specification consisting of a mesh and the texture that is being applied to it. Now, inverse rendering volume is a challenging problem in itself. And the reason for that is the existence of ambiguities in the parameters of light transport, so the absorption scattering coefficients and the phase function. Different values for these parameters can actually lead to the same measurements of the radiance field. And these ambiguities are described by something that is called similarity theory. One illustration of these ambiguities can be seen in the animation on the slide here, where the appearance of a light source seen through two translucent slabs is actually invariant to the order in which the slabs appear. Of course, this is just a very simple example. The ambiguities in our printouts are way more complex. For the optimization, these ambiguities actually create a highly non-convex solution space that is very difficult for the optimizer to navigate using gradient-based optimization. So what do we do about it? Well, it actually turns out that the volume parameterization we use to get the half-toning out of the optimization loop also helps navigating in this space. So let's look at it a little bit closer. So we parameterize each voxel of the volume as a continuous, affine combination of the base printing materials. So in essence, we print that even inside the voxels, the inks mix to a certain degree and with a certain proportion. This mixture can then be very easily mapped to scattering and absorption coefficients in the phase function, and this mapping is differentiable, so we can use it inside the optimization loop. Now, going from the absorption scattering space to the material mixture space also transforms the ambiguities. Remember, the ambiguities describe how different parameter combinations can result in the same measurements. And this transformation actually constrains the problem and helps the optimizer converge in spite of the non-convexity of the solution space. Now, remember that we introduced this parameterization to relax the optimization problem and turn it from integer programming to a nonlinear, non-convex optimization problem. And of course, the parameterization also has other advantages, such as making our method general with respect to the available printing materials. The final step to close the optimization loop is the arrow metric. It turns out that choosing a suitable one is very crucial for the results that we get from our optimization approach, as you can see on the slide here. First, the metric needs to be differentiable, which limits the selection a bit. And it also works in a general three-dimensional setting if it considers more than just local information. The delta E76 function is a suitable arrow metric, and using it to drive the optimization results in a very good reproduction of the colors. But as you can see here, the result lacks in contrast and sharpness of high-frequency features. To make the optimization favor these stimuli as well, we opted to using a combination of delta E76, MSSIM, and an edge detector. And we put them together using different weights, which actually allows us to adjust the optimization to favor certain visual stimuli. For example, we can adjust the optimization to get the best possible color image, or we can adjust the optimization to favor high contrast and sharpness of texture details. All right, so let's look at some results. Here you can see the optimization results for general 3D geometry and how it compares to the previous state of the art by Sumin and others in 2019. You can see from the images that our method is better in terms of finding the correct hue for the general color of the texture, while at the same time being quite good even in comparison with respect to the sharpness and contrast of the texture, if you focus your attention on the face, for example, of this animal, or how the spots are being rendered. Also, I can report that the computational cost is quite comparable to their approach. So I was claiming that our method also incorporates several aspects that previously required specialized solutions. So here's one use case of that. You can see here an orange slice where on the left image we let the optimizer choose freely the material mixture, and for the right image we constrained the optimizer to use a 80% transparent mixture for the pulp part of this orange slide, and you can see it results in a very natural looking translucent appearance. And here's one further use case. We call it the extended ink set. So for the left image, the optimizer was just given the cyan, magenta, yellow, black and white material to choose for mixing the inks, and on the right image the optimizer was given an additional ink which has an orange color, and you can see the optimizer is making good use of it by increasing the color rendering in the flowers and in the orange spots in the walking path. By the way, all the results that you can see here are actual renders of half-toned volumes. The performance impact of adding another material into the set of available materials is negligible. It's actually only below 1% the increase in computational time. There is some open ends that need following up. For example, optimizing objects with spatially varying translucency. The orange slice was a prototypical example of that, because it contains also the question of what metric do you use to drive the optimizer that is a cost function for the translucenciness of the object, basically. Then we have the question of aerometrics in general. There is quite some work in this area for many years, and recent work, for example, has shown that neural networks that were trained for object recognition also work very well for judging the quality of images, which is a quite surprising result. And because neural networks are differentiable, this would also work in our pipeline. Further, there is a small prediction mismatch in the way we handle color. We use RGB in our workflow, whereas spectral rendering in volumes can capture a few more effects that RGB rendering would actually not be able to. And finally, there is on this conference a new differentiable rendering technique being presented that is called path replay, radiative backpropagation, that both performs favorably in terms of the computational costs and in terms of the non-biasedness. This work, of course, wouldn't have been possible without these contributors here. There's Tomáš Ison, there is Tobias Rittich, there is Alexander Wilki, and Jaroslav Křivanek. And my name is Thomas Nindl. I'm a PhD student at Charles University and also affiliated with Berufsakademie Sachsen. Thanks for your attention, and I'm looking forward to the Q&A session.